In today's video, we are going over the basics of NumPy for data analysts. By the end of this video, you should have a good starting point to get up and running with NumPy. So the first thing that we need to do is install NumPy. If you're using Anaconda, this has already been installed for you, but if not, all you need to do is run pip install NumPy in your Jupyter notebook. Now, I've already installed this, so I'm not going to run it, but when you run this command, you'll see that it's installing down here, and at the end, you should get a installation successful message. Next, let's import NumPy. So we'll do import NumPy as NP, and NP is the alias that we will be using to access the various functions in the NumPy library. We'll start with creating NumPy arrays. The NumPy array is the foundation of NumPy. As a data analyst, most of the times you'll be using pandas for your data analysis, especially if you're dealing with both numeric and non-numeric data like strings. However, sometimes you want faster or more efficient array operations. In those cases, you might use NumPy. And fun fact for you, pandas is actually built on top of NumPy, so if you've used pandas, you've kind of used NumPy indirectly. So first, let's go over how to define a NumPy array. So to define an array, we can just define a variable, we'll call it test_r, and we'll set that equal to np.array. And to the array function, we will pass it a list. And in this list, we're just going to do a series of integers from 1 through 9. And we'll list them all out. All right, so now we can look at test_r. And when we print out test_r, we can see we have our array and it has all of our elements in it. Now, this is a one-dimensional array. It's just one row, but we can also use NumPy to create two-dimensional arrays, which are just arrays that have both rows and columns. So we'll define a new variable, test_r2d, and we'll set that equal to np.array again. And now, instead of just passing it a list of integers, we're going to pass it a list of lists where each list contains integers. So let's define our list, and then in that, our first list will be the numbers 1 through 3. Our second list will be the numbers 4 through 6. And our third list will be the numbers 7 through 9. And when we look at what's in test_r2d, we'll see we have a two-dimensional array that has 3 columns and 3 rows. So in the previous array definitions, we hard-coded the values that we wanted in the arrays, which means we just manually entered every single digit that we wanted to show up in the final array. However, there are faster ways to create arrays, and there's actually 4 functions to do so. That's arrange, ones, zeros, and linspace. So first, let's start with arrange. Now let's say we wanted to create this array without having to define each and every single one of these numbers manually. That's where we would use arrange. So we can define test array again, and we can set that equal to np.arrange. Now the arrange function takes a few parameters. The first is start, which tells NumPy what number we want to start the array at. So in our case, we want to start it at 1. The next parameter is stop, and this tells NumPy which number we want to stop the range at. And it's important to note that this stop parameter is exclusive, so whatever you put here will not be included. So if we put 9, we'll get the numbers 1 through 8 because it doesn't include 9. So if we actually want to get the numbers 1 through 9 like we did before, we'll actually put in 10 here. It also takes a step parameter, which tells NumPy what increments to increase the starting range by. So we want to increase it by 1 each time so that we get all the integers between 1 and 10 exclusive. So we'll set that to 1. And then finally, it also takes a dtype parameter, which indicates what data type you want in your NumPy array. In our case, we just want integer. Now, I will mention that the start, step, and dtype parameters are all optional. The only one you have to specify is stop. By default, np.arrange will start the range at 0, and it will take a 1 increment step each time. And if you don't specify dtype, it'll just infer the type of array you want based on your start or stop or step parameters. So now when we look at test array, we see we get the same array that we got up here, 1 through 9, but this time we had to type a little bit less than we did before. And this is also great if you wanted a range of like 1 to 100 or like 20 to 20,000. It would be really hard to go in and actually type out each integer from 20 to 20,000. Using a range is a much faster and easier way to do that. Another function we can use is called zeros, which will create an array of a specified size only containing zeros. So to do that, we can call this 0r. We'll set that equal to np.zeros. And the np.zeros function just takes a parameter that specifies the shape of the data frame that you want. So if we want to create a one-dimensional array that just has 5 zeros, we'll just pass 5 into that, and we'll just get an array of 5 zeros. So this is generally used if you know you want to create an array of a certain size, but you don't know what each of the elements in the array should be. You can use like these zeros kind of as a placeholder for those values that you fill in later as you manipulate the data in the array further in your code. I will also mention that we don't have to just do a one-dimensional array. We can also do a two-dimensional array. So if we wanted to do one that had 2 rows and 3 columns, we can specify that in a tuple where rows come first and columns come second. And you'll see now we have a two-dimensional array with 2 rows and 3 columns, and all the elements are zeros. Now, similar to zeros, there's also a function called ones. So we'll copy this, paste it down here. We'll call this ones array. And instead of zeros, we're just going to use the function ones. And this will do the exact same thing that zeros does, but you'll see it just generates an array of ones instead of an array of zeros. And the final function for creating arrays is called linspace. And this is often used for generating smooth, evenly spaced numbers, which is really great for things like visualizations and if you want to run simulations of data. So we'll call this linr. We'll set that equal to np.linspace. And linspace takes a few parameters. The first is the starting value for linspace, so we'll start it at 0. Then the next parameter is stop. Now, unlike a range, stop in linspace is actually inclusive. So this will contain an evenly spaced range of numbers from 0 to 10, inclusive. And finally, it takes the sample size you want. So the number of numbers that you want in your array. So let's just say we want 5 numbers that are evenly spaced between 0 to 10. So now when we look at what's in linr, you'll see we get 5 numbers that are all 2.5 apart from each other, and it's 5 numbers. Now, you may be wondering what's the difference between linspace and a range, and the thing is, in linspace, you don't have to specify a step size. We haven't said we wanted the numbers 0 to 10 and we want them all to be spaced out by 1. Linspace automatically determines how far apart the numbers need to be in order for you to get 5 numbers that are evenly distributed between 0 and 10. After we create the arrays, the next thing we need to do is be able to get information about the arrays and look in the arrays to see what is in them. So first, let's look at some attributes that can help us understand the dimensions and shapes and d-types of the arrays that we've created. So the first attribute is called ndim, which will give the number of dimensions in your array. Essentially, this will tell you, do you have like a 1-dimensional array or a 2-dimensional array or a 3-dimensional array, however many dimensions you have. So let's take a look at test array again. We'll access its ndim attribute. And when we print this, we get 1 because it's a 1-dimensional array. Now, if we did test r2d, you'll see that we get 2 because that's a 2-dimensional array. We can also get the shape of the array, which just tells you how many rows and columns that you have. So for test r, if we do test r.shape, you'll see that we get 9 and then nothing else because this is just a 1-dimensional array. If we do test r2d though, you'll see we get 3 and 3 because we have 3 rows and 3 columns. So that is the shape of the test r2d array. We can also get the number of elements in our test array. So we'll do test r.size, and that'll give us 9 because there's 9 elements. You'll also see for our two-dimensional array, we also get 9 because there's 9 total elements in that array as well. They're just divided up into more rows and columns than our one-dimensional test R array. Now let's look at the values of these arrays. To do that, we can use indexing. So if this is the first time you're hearing about an index, it's just a way to identify the numerical position of an element within an array, and it starts at 0. So if we wanted to get the first element of an array, we say we want to take the element at index 0 in that array. So for our case, for our one-dimensional array, if we wanted to look at what's the first element in that array, we would do test R, and in between square brackets, we can specify the index position we want, and we want the first element, so our index position is 0, and when we print that, we get that 1 is the first number in the array, and we'll see that it's also an integer. We can also use indexing to get a range of elements. So let's say we wanted the first 3 elements in the list. We would take our test array again, and in between the square brackets, this time we would specify where we wanted the array, which index we wanted the array to start at. And if we want the first 3 elements, we want it to start at the first index, so index 0. And we would specify which is the last index that we would want in the array exclusive. So whatever number we put here, that index will not be included in the range that is returned. So if we want the first 3 elements, we have to put this at 3. So this will give us index positions 0, 1, and 2. So if we print that, we see we get the elements at index 0, 1, and 2, which is the values 1, 2, and 3. We can also get the elements starting at a certain index to the end of the array, and we can do the opposite where we can get all the values in the array starting from the beginning of the array up until and not including a certain index value. So let's look at that one first. Let's say we wanted the first 5 elements in the array. To do that, we would take test R, and one way we could do that is we could do 0 to 5, and we would get the first 5 elements of the array, but we don't actually have to specify 0 here. We can take that out, and if we run that, NumPy will infer that we want everything from the first element to up to, but not including, index 5. Now we can do the opposite of that as well, where we can tell NumPy where we want to start, which index we want to start with. So let's say we want to start with index 5, and we want everything until the end of the array. We would just not specify a stopping point there, and NumPy would just infer that we want everything from index 5 up until the last element of the array. Now we can also index a two-dimensional array. The only difference is we would have to specify a row index and a column index in a two-dimensional array. So let's take our two-dimensional array, so test R 2D, and when we index that, if we want to get the very first element in the first column and the first row, we would give it those index values. So we'd want the element that's at row index 0 and at column index 0. And when we print that, we get 1. Now we can kind of look at what was in test R2D, so you can see that is the first element. When indexing a two-dimensional array, you can also just get an entire row or an entire column. So if we take our 2D array, and we just would not explicitly specify a row index, that'll give us all the rows. But let's say we want everything all the row values for the last column. So since we have 3 columns, we would want all the row values for column index 2. So here when we print that, we get 369, which is the row values for column 2. We can do a similar thing to get all the column values for a specific row. So let's say we want everything in the last row, we would specify row index 2, and we'd specify a colon here, which indicates we want all the columns. So here we'd get 7, 8, 9, which is just the last row here. Now the place NumPy really shines is in how it applies transformations to array elements. It uses element-wise operations or broadcasting, which means that for things like adding an amount to each array element or adding arrays together, we don't have to write a separate loop. NumPy is able to apply these transformations to each element automatically. These are known as vectorized operations. So first, let's look at an example where we're adding two arrays together. So I'm going to create another NumPy array called testr2, and I'll set that equal to almost the same thing that testr is equal to, but I'll just scale all these by adding 10. So now we have another array that has 9 elements. So if we take testr and we add testr to testr2, you'll see that the result is an array where each element of these two arrays was added together. So testr contained 1 at index 0, and testr2 contains 10 at index 0. So those got added together, 1 plus 10, and in the final array, we get 11. Now, for this to work correctly, the two arrays have to be of a compatible shape. Now, if we want to add these two arrays element-wise, just as they are, they have to be of the same shape. So testr2 is a one-dimensional 9-element array, and testr is a one-dimensional 9-element array. However, if I add one more element to testr2, you'll see that these two things cannot be added together because now they're not of compatible shape. So if we wanted to add together elements from different arrays of a different length, or if we wanted to add a scalar to each element in the array, so if we wanted to add 10 to each of these elements, NumPy would then use what's called broadcasting, where it would make the two arrays of a compatible shape implicitly. Compatible shapes just means that NumPy can stretch one of the arrays so that both of these line up properly. Now on this one, it would not be able to do that because you can't stretch a 9-element array to be a compatible shape with a 10-element array. If a dimension is 1, NumPy can repeat it. If it's not 1, it must match exactly. If every dimension matches that rule, then broadcasting works. So we can look at an example of broadcasting when we look at adding a scalar to the array values. So if we take testr, we can add 2 to each element. And here you'll see that each element had 2 added to it. Before testr, the first element was 1, and now it's 1 plus 2, which is 3. And conceptually, NumPy kind of treats this 2 as just an array of 9 2s, and it takes each of those 2s and adds it to each of the elements in testr. We can also filter NumPy arrays if we want to look at the rows or the columns or just the values in the array that are meeting a certain condition. So if we wanted to look at all the elements in testr over 5, we would do testr, and in between square brackets, we would specify the condition. We would do testr greater than 5, and when we look at that, we get all the elements in testr that are greater than 5. We can also do that with our 2D array, and again, we get the same thing, just all the elements in our 2-dimensional array that are greater than 5. Now, there's a few functions that you'll see used quite commonly when people are using NumPy. A lot of those are descriptive stat functions. So NumPy has a mean, median, standard deviation, min, and max function. So we can take a quick look at those. We can do np.mean, and we can pass it an array that we want the mean of. So we'll take the mean of testr, and I'll print testr out here so you can remember what's in there. So here we get the average, or the mean, is 5. We can also look at the median of testr, and you'll see the median is 5, which you can go and check that the median is in fact 5. We can also get the standard deviation, which we get is around 2.6. We can also get the minimum value, which we'll see is 1. And we can also get the maximum value, which is 9. Finally, we can also reshape the array. This is used a lot with machine learning. It'll reassemble the elements in the array so that it fits a specified size that you provide it. So let's say we wanted that one-dimensional array of 9 elements to actually be reconfigured into a 2-dimensional array where we have 3 columns and 3 rows. We can actually do test r dot reshape. And we can specify we want it to have 3 rows and 3 columns. And what it'll print out is that 2-dimensional array. Now I'll mention it doesn't change it in place. So if we look at test r, we'll see that's still that 1-dimensional array. To actually get it to save this reshaped array into test r, we do need to reassign it. So if we run that, and then we look at test r, we'll see that test r now stores the reshaped 2-dimensional array. All right, so that is it for the overview of NumPy. Now, I will say as a data analyst, I generally use pandas more than NumPy. However, if you have data that is all numeric and you want to efficiently process that data through things like vectorized operations, for example, NumPy is a good library to know about. If this video helped you get started with NumPy, I would love it if you let me know by leaving a comment or liking and sharing the video. And of course, don't forget to subscribe to the channel for more data analytics content if you haven't already. Thank you so much for watching this video, and I will see you in the next one.